Okay, so autoencoders. So from last week, we learned that neural networks, we started with perceptrons, moved on to ANNs, and then a plain feed-forward network. And then we understood what is feedback, what is back propagation, how weights are updated, what are iterations, what are epochs, and what else? How training happens, and we understood what are deep neural networks, right? So essentially, you can add more and more layers for the network to learn more and more complicated features. And as a result of adding more and more layers, the learning becomes more efficient, but so does all the other problems that come with deep learning network. That's the context in which we saw three main issues with deep neural networks. The first was vanishing gradients. The second was optimization issues. The third was overfitting. Overfitting is a classic neural network thing. So whenever you use neural networks for structured data, just 1,000 rows, um, and if you split into train and test, that's 80/20. So that's just 800 rows. So you are building a model with 800 data points, neural networks. Um, that that will very likely overfit if you have a deep neural network for that. Usually the rule is you don't go beyond two layers for structured data, um, unless there is high dimensionality or high causality, stuff like that. Usually, deep neural networks are not required for structured data, especially when the number of rows is less, like 2000, 2005. Only if there are like 1 lakh, like 100,000 or a million rows, is when we would really want to go for a neural network for structured data. So when you do that, the overfitting obviously becomes a problem, and a way to reduce overfitting is regularization. We discussed two things to control regularization. One was dropout, and the other was, what was that? Let me go to one slide. So one was dropout, and yeah, dropout and batch normalization. Oh yeah, we discussed dropout as a way to reduce overfitting. Yeah, and adding noise to the data. Sometimes that works as well. And then we discussed optimization issues. So optimization is basically the other way to do normal regularization is to add patch normalization. And we discussed different ways in which we can control for the optimization. We saw different variants of gradient descent. So we introduced the concept of momentum. So that's just stochastic gradient descent with momentum, and then RMS prop, and finally Adam. And we finally kind of fixed that Adam mostly works in most of the cases. The first problem was vanishing gradient, for which we decided to use a different activation function, something like ReLU. Okay. So some of the take home or the prescriptions that we discussed last week was Uh, there are only three common activation functions: sigmoid, tanh, and relu. The sigmoid and relu are probably the most common. If you go deeper, then you can go for relu. If it's a shallow network, you can stick to sigmoid. Can stick with your sigmoid activation. Um, and then the gradient descent, we can go with Adam wherever required, or we can just use RMS prop. We do add a batch normalization layer every now and then. That just reduces the necessity to deal with big numbers, huge numbers with big ranges. So that fixes part of the problem. We add dropout every now and then in between layers so that um, the network doesn't overfit, right? So these are some of the kind of prescriptions, some of standard procedures that people use while building neural networks. Last week we discussed the recent framework. So that kind of closed one full chapter in neural networks. So now, when we actually start building neural networks tomorrow, we'll try and understand what is training, how long does training really take, uh, um, you know, what can go wrong while building a neural network? What are parameters? What are hyperparameters? We discuss these, but we will actually see them in real time tomorrow when we do our first lab. Okay. Uh, Everything that we are going to discuss from now on is going to be based on these foundations. Okay. So a recurrent theme will be weights. We are going to say, okay, the weights are fixed, the weights are saved. We can change the parameters. There are so many nodes, there are so many hidden layers. So we are going to use these terms as if we are familiar with those terms. Okay. So we should be really familiar and we should kind of get used to these jargons that we learned in the previous sessions. Any questions still there? Okay, so there are no questions. We'll continue. Um, Today's topic is autoencoders. Okay. The autoencoder is a very unique kind of neural network. The concept is really, really simple. The concept is really, really simple actually. Um, Again, autoencoder is a concept which you will keep coming across. Okay. So we will revisit autoencoders in multiple situations in the future. And I think that's part of the reason why this was a full 3 hour session. But I've decided to break it down into a very, very short introduction to autoencoders today. Like what is it? What is it capable of? When we do images, when we start dealing with image segmentation, we will again revisit autoencoders. When we start doing text data, we will again revisit autoencoders and see how autoencoders are useful in a number of situations, right? So although the core is only is the topic autoencoders, we are going to be doing it very briefly and further, when we do other topics, we will see how the autoencoder naturally fits into different use cases. Okay, so don't worry if I'm going to just talk about autoencoders for what 15-20 minutes. That's completely fine. I'll explain what is autoencoder. I'll take one use case and I will try to explain what that use case is. And then we will quickly move on to the next chapter. Okay. Okay. This is a schedule we received from upgrade team. But why can't I see a schedule? Can just see? Okay, I'm not able to see the schedule. I can only see the
Yes,
test.
I get there is a challenge. because the admin team has, actually uh, removed the rights to share any file on this chat. So I'm trying
Ah,
to share it in different way. Just 1 minute. I'm trying to do that.
no problem. No problem.
Just I'm almost done.
No problem.
Uh, just check that whether it is visible also.
Well, says that this doesn't look correct. Okay, you
Yeah, yeah.
guys reset it is for older kids. Okay. So you guys reach a consensus and let me know. I'll start with the
No,
current
no. Now
session.
he was responding to the old one. Now I have uploaded the current one. You'll be able to see this. It starts from 10th May and ends at 28th June. Right?
Okay. Sure. Okay. Well, this is pretty much what we are discussing, right? What we are doing currently.
Yeah, yeah. But Rayo had some queries, so I posted from whatever I had.
Yeah, this looks like the version that I have. Maybe there was some mistake, and maybe the first version was some old version that they shared by mistake.
Yeah,
This looks correct, actually. This looks consistent.
yeah. Rayo, you have any questions on this? Because this is what Sam also has shared on our WhatsApp group. Okay, I think Rayo is not. Okay, thanks, Professor.
So, okay. So the autoencoder is basically a fancy name for I'm giving a set. So till now, the neural network that we used was basically we have a set of input features, and then we have a couple of hidden layers, hidden neurons, and some sort of an output. Okay, sigmoid, and this is an ANN. All it's all fully connected. Okay, so four input layers, um, four input features, two hidden layers, five neurons in the first layer, three in the next and last and output layer. Right. This is the neural network that we have seen till now. Our assumption was each node, each neuron in this input this thing in the hidden layer is going to do one particular job that it is specializing in. So as a result, whatever um, whatever features are there, the neuron is learning to combine those features in as many non-linear ways as possible. Okay, in as many non-linear ways as possible and represent the data efficiently. That's the assumption on which we are working with the neural networks. Now, if you see here, the autoencoder is going to be very similar, but it's going to be a couple of input neurons. Okay, and a couple of trainable parameters. So one, two, three, and then one, two, three. Usually after this, there's going to be an output layer, which basically says what is the output. Like if it's a logistic regression, then if it's a two binary classification, we can put a logistic regression. If there is a multi-class classification, we can do a softmax. So depending on that, we have an output layer. Okay. But the autoencoders are going to be slightly different. What has happened in this neural network until now? We have a given, we have some input features, right? And these nodes are, what are they doing? What are these neurons doing to the input data? Hidden layer one, hidden layer two. What's happening to the data?
You're assigning the weights.
Assigning the weights to do what? Let's say without the output layer, let's ignore the output layer for a moment. Okay. Uh, what are these hidden layers actually doing?
They're transforming into some form of representation.
Yeah. So we give a set of numbers, right? And we are hoping that this neuron is seeing all these numbers. It is doing some transformation, and it is giving those transformed numbers to the next neuron, right? What will happen if I add, instead of one output layer, I am going to have three hidden neurons here.
Instead of getting a compressed representation, it will get expanded.
Yes? Did that make sense what Nia said? Nia says that we are giving some set of input numbers, okay? And the hidden layers, basically they are trying to represent those numbers in a different feature space. And since I'm reducing the 5 to 3 and then 3 to 2, the network is basically combining these numbers and it is trying to make a complex representation of this. Okay, so everything within the input features, the relationship between the columns exists, but in its own world, in its own compressed whatever form, which we probably cannot understand, but which the neural network thinks that it can understand. Okay. Based on those compressed representations, it is making a prediction. That's the regular neural network. But instead of an output layer, if I again give three neurons, and if I connect all these to all the three neurons here, right? What's going to happen? The compressed form of the data, okay, what the two neurons were able to represent is now given to these three neurons. So basically, we are saying, okay, I have a set of numbers, which is, I have a story which is told by five people, right? And then those five people need to pass it on to a set of three people. Okay. So this guy is going to remember the story in whatever way that they can. right? And that is going to go to two people, right? So now the story is now in a very compressed, very paraphrased form. Now I am connecting the story to three people now, and I'm saying, okay, now expand it, right? So what was represented by two neurons, I am now telling represent it using three neurons. Okay. And finally, I am okay. And finally, what I'm saying is instead of the output as a binary classification or whatever, I'm giving my original story, which was told by the five input layers. Okay. Now, what's happened in this whole cycle is we have a couple of data points, okay, which was efficiently represented by three neurons. Okay. And then we further compressed it to two neurons, thinking that, okay, these three neurons will now if represent this data efficiently. And then in the next hidden layer, we are expanding the story and we are giving five empty points in order to represent it. And we are hoping that whatever input we gave will come out correctly. Why? Because if this compressed representation is an accurate description of my input data, what comes out of this network will be my original data. Did that make sense?
No,
Was that?
no, it didn't make
So
sense.
It didn't make sense. Okay.
is
Uh,
are
what's
you
that?
trying to reconstruct the inputs again?
Exactly. Correct. That's exactly
Thank
what I'm trying to do here. So
thank you.
instead of making an output prediction as to yes or no, or category one, category two, or a regression output, I'm trying to reconstruct whatever data I gave him. Okay, so I'm hoping that this guy, this will be this.
Professor, but it need not
Okay.
have to be exactly
And
the same, right? It can get transformed into similar another four sets, right?
ah, correct, correct. But something very similar to what we gave in the input.
Yeah.
Correct. It need not be exactly. Okay. So that is my autoencoder. So during training, instead of giving a correct answer as as in terms of a correct prediction and saying yes or no, I am giving the input data only as the output data. Okay. So what did I achieve through this? I achieved a pattern representation. Okay. So I achieved a way of representation rather than a correct kind of a prediction. If my whole data set is represented efficiently using these two neurons, okay, then what I'm actually telling is I do not need five people to do the job. This can be done by just two people,
Wow.
right? And that is a part of the training. I will train with two neurons in the so this is called the bottleneck. Okay.
And this,
So this I will train with two neurons in the bottleneck or three neurons or just one neuron and see which number represents the input, which number in the bottleneck actually is able to reproduce the input data efficiently. So now I'll say, okay, I actually do not need these five neurons to do the job. Just one neuron is enough, or two neurons are enough.
and this is what effectively we were trying to do when we were dropping out also, right, Professor?
in a way, you can say that, okay. So in dropout, what did we do? We were trying to,
At the instances
hmm,
when that neuron gets dropped, like the other neuron tries to compensate or pick up its responsibility, and it was able to do by the time, like these weak neurons weights used to get diluted in the further iterations, and because of that, like we were in a kind of condensing the network, right?
so we were not condensing it
Yeah,
really.
yeah.
We were trying to reallocate the job to multiple neurons.
Yes. So what might happen is that neuron will get freed up from this job, and it may pick up some other responsibility because we are not trimming down.
Yes,
Basically. Yeah.
correct, correct. So it learns some other tasks.
Hmm.
Here, actually, we can do dropout in autoencoder also, but that serves again the same purpose. But you can include autoencoder, can include dropout here, but I'm not sure if this is the same story as dropout or in any way it's connected. I'm not able to make the connection.
Okay, got it. Got it. Yeah. So technically here we are constricting the
Hmm.
center model so that like we see that what is the optimal representation required to represent it, right?
The optimal number of neurons required to represent my input data.
Yeah.
Okay. Yes. So this is while training the neural network. So what basically happens here is, I mean, one of the use cases here is actually I can I can give a number of input. I can give a number of input data here. Okay, and I can actually reduce it to these neurons, which means that if you take a business case, I'm giving a data set that has probably 25 input rows, right? By combining all these input features in some form, if I'm able to get only, if I'm able to reproduce the data with just 4 or 5 neurons in my hidden layer, then what I'm saying is there are actually 4 clusters of customers, right? There are only 4 stories in the whole database, and the whole data set can be represented using those 4 stories, 4 or 5 stories, depending on how many neurons are there in the bottleneck. Now, did it make sense after all the discussions? Suvir?
So can you give an example of the practical implementation of this? Maybe going
Ah,
back to the examples that we've been
yeah, yeah.
discussing, or a fresh
Well,
one
yes.
here may help
Yeah, yeah.
contextualize better.
Yeah, I have some examples, but conceptually,
Yes, conceptually, yes.
okay. So whatever we discussed in our previous issues with neural networks is going to stay with, is going to actually uh, be there for autoencoders also. All our issues with vanishing. I took a neural network that is just 3 layers deep, but I can, I mean, if I have like 100 different inputs, right? So if I have 100, up to 100, I can reduce the neural networks. I can make it compact. I can start with um, okay. So I can start with a first hidden neuron, hidden layer with I started with 100, right? So I can have 50 here. So I can have 50 here, and then 25, and then come down to 10. So that's my bottleneck. And I can again slowly increase it to 25 and then increase it to 15 and have 100 in my output again. Okay, so the deeper I go, the more my number of input neurons, the deeper my autoencoder layer will be. So bottleneck is only one layer. Yes, usually bottleneck is only one layer. Correct. Okay. This is the overall architecture of my autoencoder. Okay. Let me go to the slides again. Okay. So conceptually, I have an input layer and then a couple of hidden layer and the output layer. The input layer and the output layer are will match exactly. The number of neurons in my input and the number of layers in my output should match perfectly. Okay. So in principle, it's basically a multi-layer perceptron. Uh, it is a neural network basically, again with back propagation, learning and all that. But what are its properties? Basically, in a regular ANN, the output is going to be a y, which is going, and we are going to have a y dash. Here, the output is actually going to be the input data exactly. Okay, so if I have like 8 columns in my input, the same 8 columns I'm going to give as the output. Okay, so what happens during training? It learns the feature representation basically. Okay, so it learns what goes into the first hidden layer, what goes in the second hidden layer. All that is what is happening during the training. So if I were to design a campus abnormal behavior alert system, exactly, my approach would be as follows. I will use AutoML to help design an efficient model architecture. I've then reduced the suggestions provided by AutoML and ensure they align with my requirements before building the model using neural networks. I would train the model using large data set of video clips. By applying an autoencoder, the system would automatically learn key features from the data. Reconstruct the input figures, compare them with the original inputs. The model will continuously adjust its weight based on reconstruction error. During the training process, I will be mindful of potential side effects of neural networks such as bias evolution and mitigate these issues. Is important. Define the system supervised by labeling normal and abnormal, allowing the model to improve its classification capability. Okay. I am given from yeah, correct. Yeah, correct. That is a correct description of what an autoencoder is actually expected to do. So now, from autoencoder, it has not only learned some sort of a feature representation, it has learned what a correct data is going to really look like. Okay. Right. So a vanilla autoencoder basically moves the input data into a lower dimensional kind of a hidden space. And we are just asking what happens when we try to squeeze the data through a bottleneck, right? And try to reconstruct it on the other side. So if I take the example of an MNIST data set, I have 60,000 examples of these handwritten digits. And as far as images are concerned, for now, let's consider that each pixel is going to be an input. So a 28 by 28 image is going to have 784 pixels. So there are each image is 784. Each zero here is a 784 pixel. And see how I'm constructing this autoencoder. So I have X-train. X-train, I'm doing a train test script actually. And I'm doing some pre-processing. This is, you see, I'm dividing all the values by 255. This is part of my normalization, right? So where I want to reduce all the numbers between 0 and 1. In any image data, all the pixel values are going to vary between 0 and 255, 256 values. So 0 is completely black. That pixel is completely black. 255 is the pixel is completely white or as bright as it can be. So when I divide a pixel by 255, I'm basically reassigning a number to the existing pixel value. 255 becomes 1, 0 becomes 0, right? So that is a standard pre-processing that people do. And as you can see here, my input is whatever the input image. I'm giving the shape and dimensions. One thing I didn't expect is, I didn't explain is basically, I will quickly go to the whiteboard. Okay. So anything before the bottleneck is going to be called an encoder. This part is going to be called the encoder, and the part right after bottleneck, that's going to be called the decoder. This part is going to be called the decoder. This part is going to be called the encoder. Okay. So anything that happens here is happening in the encoder space. Anything that happens here is happening in the decoder space. You would have heard the word encoder decoder in a slightly different context in LLMs. We will come to that. There is some relationship, but there is also a lot of difference between these two. So let's not worry too much about what these terms mean in LLMs. Okay. But for now, in case of autoencoder, anything that is there on the encoding side before the bottleneck is going to be called encoded path. Anything that happens on the output side in the expansion phase after the bottleneck is going to be called decoder. Okay. So okay, so that's what I have here. The encoder vector dense. Remember how in the previous constructions we kept on adding. We said sequential. Remember the term sequential. So we added these layers one after the other in sequence. But here we are kind of fixing what layer this particular layer is going to talk to, what previous layer this is going to communicate with. So the name is encoder, and this is related to this layer called X here. And what is X? X is my input layer. Okay. Now this is the bottleneck. And then there's a decoded vector where again I'm saying dense 28 by 28. Where is this coming from? Is the same input or as the number of pixels in my input image. Okay, sigmoid activation. I'm going to just call this layer the decoder layer, and this is going to talk with the encoded vector, which is right here. Okay, so this is basically one input layer, one bottleneck, one hidden layer, and one output layer. That's all. Just three layers, including the input and the output layer. That's the architecture of this neural network. So, what did we hope through this? We are hoping that if we send an image, it will be able to reconstruct the same image, right? Because that's what we want the network to do. Okay, we have an input data which had a dimensionality of 28 by 28. We reduced it to 32 dimensions. So that basically means that in order to represent a 784 dimensional image, we actually only need 32 dimensions, and that is actually doing a pretty good job, right? We are getting the 5, we are getting the 9, 4, all the numbers are coming out on the other side very close to the input. Okay. So this is just like a non-linear PCA. What happens within the autoencoder is basically dimensionality reduction. So what we did in PCA was, if x1, x2, these is my two of my input features, and I'm trying to do a PCA. So it is the transform space, and I have the reconstruction error. Whatever happens, PCA can only still draw a straight line, right? So it is still linear. So let's say that there is a data point here, and this is my reconstruction error. What we achieved through our autoencoder is, instead of drawing a straight line through these data points, we try to do a differentiate. So now whatever reconstruction error we had for PCA, that reconstruction error has reduced, right? So just a high dimensional, just a non-linear form of a well-known algorithm uh, like a PCA. So while training, we just show we explicitly say that uh, uh, if there are 100 input features, I will give 100 blank spaces in my output. So during training, it learns to represent the 100 features efficiently using this bottleneck and slowly reconstruct it. Okay. So any questions here till here?
Professor, how do we arrive at the optimum number? Because in the clustering, sometimes like when three clusters are optimal, we see that four may not be optimal, but five may appear to be optimal. So we have that elbow kind of a test. So here, how we will be getting to know the optimal neurons?
Yeah. Again, that only comes from trial and error. Okay. Uh, so we try to find it using, there are metrics, there are error scores, something called Silhouette score. So we'll probably discuss it in tomorrow's lab session. Okay, so tomorrow's lab session is mostly a structured data. I'm not going to start with images. So we will take one data set and we'll try to drag and drop, and we'll try to see the metrics and all that. Okay.
Sure.
So conceptually, is it clear? So what has happened here basically is we have learned to represent a complex data form using minimum number of features, right? One of the applications of this is denoising an image. So we can we can basically uh, tell the network that, this is my input data, okay? And we can manually clean those images. There are actually denoising algorithms, right? In computer vision, where you can reduce the noise and you can actually convert this image into this image. Okay. So to the input layer, these set of numbers go, the one on the top. Okay. For the output, I will show these numbers, the clean version of the numbers. Okay. So basically, the network will learn to find out which is noise and which is an emerging pattern in the data set. Is that clear? So essentially, it is acting as a denoiser.
It kills some info, and here the killed info happened to be the noise.
Yes. No. So, yeah, correct. That is, but I would like to add one little thing more. The autoencoder basically learns patterns, right? Using a number of these examples, it is learning patterns. And when it learns patterns, it is also learning what is noise. Okay. So we are training the network to identify only the most important critical things in the data set, which define the patterns in the data set. Anything else is noise, right? So when we force it to work with just 30 neurons or 30 dimensions or the 20 or 15 or whatever, how much ever we are compressing it, okay, it is now forced to get rid of anything that is irrelevant. It is only rewarded only if it retains the most useful parts of the data set. Okay. And as it happens, the most useful parts of the data set are the clear patterns that are emerging within the data set. Why? Because the noise in one number will not be the same as the noise in the other numbers. Right? Noise is basically random. When things are random, there's no pattern to it. Even if there is some emerging pattern, it is probably not so useful that it helps in reconstructing the image. So as a result, the autoencoder automatically cleans it, automatically gets rid of identifies the noise and says, hey, this part of the image, this thing which I'm using right now seems like noise. So that's not helping me. So I'm not going to waste one neuron, one resource, which is really precious in autoencoder. And it's going to say, I'm going to get rid of it.
Understood, Professor. Thank you.
And if everyone else, the session is unusually quiet today. Okay. So as long as the images are concerned, autoencoders help in denoising. They help in auto-filling. Uh, I mean, previously before, transformers were a thing, autoencoders were really useful in filling missing information. Now, one of the main uses of your autoencoder, and that's what was there in the chat, is anomaly detection. Okay. So anomaly detection is basically in an autoencoder. So I told that the autoencoder is basically trying to find the pattern and the most important pattern, right? So anything which doesn't fit into the pattern is easily flagged by the autoencoder, right? So let's say that there are 500,000 credit card transactions, which are legit, which are correct transactions, and there are probably 500 fraud transactions. There's a huge data imbalance here, right? So as a result, any model that you are going to build is going to have very high accuracy in finding the correct transaction, but it's not going to find the bad transaction, fraud transaction as efficiently. Why? Because it had only 500 data points to learn from. Okay. So autoencoder is one way to address it. So instead of doing a binary classification, people say, okay, you learn whatever is correct transaction. Okay. Anything that doesn't fit in this pattern is flagged as fraud. Okay. So it is able to identify anomaly, like how in this case, noise is actually an anomaly, right? It is able to identify the anomaly and it is able to get rid of. It is not really identifying the anomaly per se, the noise per se. It is actually learning the features. It is learning the eyes and the nose and the hat and feather and all that, right? Denoising is a side effect of it learning the perfect pattern. So similarly, in anomaly detection, the neural network basically learns what a correct transaction should look like, right? So as a result, it is able to flag any pattern that doesn't fit into its learned pattern. Okay. Previously, historically, it was used for text translation, for generating images. For generating, like for example, if you don't know what's happening here, for autofilling, for generating, what you call as generative models here, the ancestors of those models. Okay, to feature engineer. All these are the historical use cases of autoinference. But it is still very relevant in anomaly detection even today. Okay, because neural networks are pretty fast, and we need when the thing with anomaly detection, like for example, credit card transaction is the fraud should be detected with very little latency. When the fraud is happening, it should get detected, right? So if we have to use a complicated model like a transformer model or something big, the latency is always an issue, right? So deploying a neural network is much more easier while doing anomaly detection. So if people still use autoencoded models for anomaly detection and a little bit for denoising also, case solution.
So I think clearly this section is becoming the beginning of the generative part for us, which I think will become the next section of our conversation from, I guess, the next
Exactly.
module
Yeah.
onwards. And I guess here we'll start seeing a very big shift from what we've learned from a data processing standpoint to a generation standpoint, and there'll be a lot of blanks that will get filled in for us academically. Is there something particularly about the characteristics of the neuron that change significantly, that are able from a computational perspective, that's something that we need to know about, that will help us understand this switch now from the graduation that we've come from the machine learning side, now moving to the DNNs, ANNs, etc., ANNs, DNNs, moving to now generation? Because I think this slide has now clearly pointed us in this direction, and this segueing into generation, into this generative part. So is there some characteristic of this, of this part that is unique, that separates it from what we've covered in the last 6 months, and bring us to this point? Sorry, it's a little vague question, but
No,
I
no,
think,
no. I think that is the beauty of neural networks. At the heart of it, it is only the weight updates. It is only back propagation. It is the gradient, good old gradient descent, forward pass, iteration, learning, epoch. That is the basic actually. So if the question is there anything fundamentally different? The answer is actually no. There is the way the weights are updated, the way the training is happening, everything is very similar between what we have done till now and what we are going to discuss from now on in any type of neural network for that matter.
Got it. I think I meant it more from the perspective where I think this is the first time where we are looking at the example where the output is a non-binary output, as you called out right in the beginning of this class itself as well, you know, which is why I asked this question, I guess.
Okay. So, so you are telling that as I said, every problem is either a logistic problem or a regression problem, right?
That's right. That's right.
Yeah, this is also a logistic regression problem. I tell you how. You know, for filling up for or I'll say it's a regression problem. For filling a pixel value, it has to vary between 0 and 255. So it has to pick a number between 0 and 255, right? So it is still a regression problem, but at a pixel level.
Got it. Got it.
Yeah. So that I'm going to stick to what I said. See, that's the beauty of these things. At the heart of it, these are pretty old and very established and simple techniques actually. Okay, if I go to the previous example in the MNest, um, and I expected a question there, but it's okay. The activation is actually sigmoid, right? Sigmoid is basically a binary, 0 or 1. And
Right.
if you see the images are actually 0 and 1. These are not grayscale images. These are binary images. So the pixel values are either 0 or they 1 or they go to 1. So at every pixel, it is actually deciding if the pixel value should be 0 or it has to be 1. That's what is happening here.
Got it. Understood. Okay. Got it. Thank you.
So that was the logistic problem. And this one pixel filling here is a regression problem basically. Okay. And if I come to it, if I use structured data also, it is only either of these two.
Got it.
Yeah, yeah.
Thank you.
Okay. So quickly, uh, I'm looking at an example that I made, but it didn't come out the way that I wanted. So, here it is. Okay. So I want to do a customer segmentation with autoencoded users, right? So what I have here is a data set which has age, income, spending score, product usage, and all these things. A lot of other features that go into a data set. So I'm going to use autoencoders for clustering, right? So I have customer data, and I'm going to use an autoencoder approach. And the clustering is actually done in the latent space in one of the hidden layers. Okay, so instead of explicitly building a clustering algorithm, I'm going to let the neural network uh, do the segmentation in the bottleneck layer. Okay, so I have all these customer data, and this is what my data is going to look like. I'm not going to go into the details because that's going to sound like tomorrow's lecture then. Okay. See, this is my input data, correct? My input then, which is my actual input data. Okay, and I am choosing to. This is my first layer in my encoder space. Layers dot dense 8. I'm using activation value Why? Because I'm going slightly deeper. This is what we can play around with. Is really needed here? Can we go with sigmoid? All that is there. Customer input. So customer input is basically my, if I go to my input dim, which is X underscore customer, and what is X underscore customer? That is my actual input data after some preprocess. Okay, so this is my input data. This is my X underscore customer, and that's my input layer. That is directly in communication with my first encoder layer, which has 8 neurons. And then latent dimensions is 2. I'm making a bottleneck with 2 neurons. This is is talking to my first encoder layer. Okay, and this need not be X actually, it can be Y, can be any variable, just rewriting the old variable. If it's confusing, don't pay too much attention. I can actually call it Y and it's going to still work. So again, layers.dense 8. You see this number completely agrees with this number. Okay, and this is in communication with the latent layer, which is the bottleneck layer. And this is my output layer. And here you see what I'm doing, input dimensions. Whatever is my input dimension, I'm giving the same dimensions here as well. Okay. And the activation is linear because my data set has all these different numbers. Okay. And that's why I'm having a linear. And I'm building my model with that. This is how I'm compiling the model and putting things together. Okay. And my loss, I should have gone more epochs probably, right? Because I should probably change some of the parameters. Probably 2 is not enough. I should probably ask this to you. What do you think of this training loss?
There seems to be a good amount of gap between the training and validation.
Yeah. The validation loss is higher than the training loss. So could be a little bit of overfitting, but if you see the network didn't really converge actually, right? So I don't know. I might change some of the parameters and see if this is the best that can come out of this.
Yes.
Let's not worry too much about that. That's for tomorrow. Okay.
But
So
technically,
now,
that graph
yeah,
indicates that it's a overfitting, right, Professor?
yeah, correct. Because the training loss is much lesser than the validation loss. Okay, so there's some overfitting going on. But I would also see if this line is actually true. If I add some dropout, actually this line might come up. It might be somewhere over here. So yeah. Okay. So essentially, I'm using a k-means to see how well this data set fits with the uh, uh, number of clusters. Okay. So what did I learn from this autoencoder? Here is, well, for a latent dimension of 2 with 2 neurons, the network is actually able to do a reasonably good job. Okay, so instead of starting completely with a different number, like, starting with a number like 10 customer segments or 15 customer segments, now I know a ballpark number which I can use for my K-leads. So I'm using like doing a regular K-leads, and I'm trying to see how how many customer clusters I am actually getting. Okay, so I mean, the number of customer segments that I'm going to get in my auto info latent space, I can see it. So uh, okay. So we will try to construct this tomorrow in a slightly better way. There is some information which I thought was there here, but it's missing now. But that is basically what my auto encoder is capable of giving me. So the fact that it was able to reconstruct the whole data set using just two of the between two neurons in my hidden space gives me some ballpark figure for the number of customer segments that can exist here. I can of course do a better job here, and I can probably do a 3 or 4, and I can come up with a better number. Okay, that is the use of autoencoders. Another use is basically what I showed before. The reason I'm not paying too much attention to it is it is constructed using convolutional neural networks. So I don't want, since I didn't cover it yet, I don't want to speak a lot about this. But basically, what we are doing is we have a clean image. We are deliberately making it noisy. Okay, so we are actually adding noise, uh, just so that it learns to denoise, just so that the network learns to denoise denoise from the training. Okay, so again, this is my construction. As you can see here, I have my first layer, my second layer, and this is my final encoded layer. This is my bottleneck layer. So I'm saying I can probably represent, I'm pushing it really hard, and I'm saying that just a 2 by 2, like using just 4 features, it will be able to represent my input, my original input image, which is 28 by 28, 784 features. That's really pushing it hard. And again, this matches with this layer, this matches with this layer. This is my input layer. Okay. And how will it work? It was able to do a pretty decent job, right? So my original image, I added noise to it, and I gave the noisy image to the network to train, and it was actually able to retain only the consistent features. Okay, and it found that all these unnecessary pixels here, they are all noise. Okay, so basically it was able to denoise the image. Any questions still here? Okay, if there are no questions, I think we can take a break now. Let's come back in around 12 minutes, 12 to 13 minutes. Sounds good?
Yes, Professor.
Yes, Professor.
Okay, thank you.
I missed something somewhere.
Okay.
Thank
Okay, sure, yeah. So, for those who, so you do have, everybody has an account, right? I don't have to start from there, I hope. From how to set up an account, how to use your $150 credit. I don't have to start from there.
Yeah,
Is
we
there?
have account everyone, yes.
Okay, so if that is there, you just have to go to ml.azure, select a resource group, and you'll find this. Okay, that's doable. Okay.
Okay.
Now, part of it we will be doing in this thing called collab. Okay, so we'll create a new notebook in Drive. I hope everybody has a Gmail account.
Yes, Professor.
Okay. So we don't have to code anything. What I will be doing is we might have to What is a good way to share a file with you?
Can we share on Teams? Can we share on email and then we can circulate it on the
Google,
WhatsApp group?
Okay,
Google,
then
Google Files, Google.
Google Docs. Okay. So I'll try to put it in a drive and I will share the link. I'm wondering if okay, I'll see. Okay. Anyway, so maybe 15-20 minutes before the session starts, I will do both. I will send it to one of you and you can circulate to everyone. And I will also put it in my drive and I will share the link to the drive. And I would not expect you to code from the beginning, but what would be really interesting to learn tomorrow is like how I had in my notebook. So if I have a code like this, I might ask you to change the yeah. So I would ask you to change the activation function here. I might ask you to change the optimizer. I might ask you to change the loss function. So stuff like this, I might ask you to make some edits, and that will be very, very manageable. I wouldn't expect you or anyone in DBA level to actually code all this. Okay, even I'm not going to code it. I'm going to give the instructions to Codex or ChatGPT, whatever, and it's going to give me the code. But I will leave some space holder here so that you guys can notice the difference between the different sigmoid functions and all that. So we'll be switching between these two for tomorrow. And one other thing that we started doing last week, but we did not complete was the playground, the TensorFlow playground. How many of you got a chance to continue where we left off after last week's session? I know you guys are working professional and it's very difficult to spend time in it in this outside of the session, but did you get to explore this website? No?
No, Professor, actually.
That's fine, that's fine. So this basically I actually wanted to start with this, but I forgot that we were in the middle of this last week. Okay, so what is the problem we are solving here? We are solving a classification problem. Um, let's start with the generic learning rate. You can actually do this simultaneously on your screen. You don't have to look at me doing this. Um, so let's start with no hidden layer and just one neuron, and let us see what happens. Okay, so what this neuron is capable of doing is it's only capable of drawing one vertical line. Okay, so the question is one vertical line enough to describe this data set? Well, it depends on. I think it does a decent job here, right? Ideally, I would want one diagonal line, but I think one vertical line is like okay, I can live with this, and one horizontal line. Let's see if that does the job. Let's go really slow. You see how I'm adjusting the learning rate. This is going to take a long time to train. So you can see here, you can see how the loss changes with how the loss really changes with the number of epochs, right? And this is with a very, very slow learning rate. if I'm going to increase it slightly and reset, now it is slightly faster, right? It's going faster, but again, because of the very nature of the neuron, this neuron is capable of drawing one horizontal line. That's it. Okay, so it's drawing that one horizontal line wherever it thinks best. So again, I'll probably live with this, but it's not perfect. So I add one more neuron here. So I'm trying to see if the data set can be described by using two input features. So now I'm getting a diagonal. So the diagonal line is basically a combination of this vertical line and a horizontal line, right? So this probably best describes this data set. Now, if I'm going to change the learning rate, it is still going to happen, but it happens much slower, right? So that's my first neural network with very simple data set. Okay. Now let me slightly complicate the data set. Now there are different clusters here. I have probably two clusters, but they're divided in the four quadrants of data. Okay, so let me see what we can do with this. We have classes of 10, and can anybody explain what's happening here? The training loss is 0.5 and it's not getting any better, and you cannot see any line here. So what's happening?
It is permanently sticking to one of the decision.
Yeah,
And it's always classifying either blue or orange.
yeah. So it's basically not able to describe the data at all, right?
Yeah. Yeah.
So let me do some transformation here and try to see if any of that is going to work. Again, yeah. So as you said, we can see only the orange shade here, which means that it's trying to fit the orange data point, but even that is not happening perfectly, right? And it's kind of stuck again at 0.5. So I'm going to add a different transformation, x2 squared, and let us see how that works out. So I'm changing my learning rate. Still nothing. Can try to change my activation function. How activation function doesn't make much of a difference here because this is not an gradient. This is not an vanishing gradient problem, right? This is actually a feature problem. It's not able to generate enough features to describe this data. Okay, so I feel that the only solution in my hand is to add some hidden layers. Okay, so I'm going to start with one hidden layer with one neuron and see how that goes. Now, mentally, what I'm doing, I have one vertical line and one horizontal line, and I'm seeing how those two lines can be combined to give me some sort of a shape. Again, I'm changing the learning rate, the activation function. None of that is working. Why? Because by nature, this data set is very complex. So let me add one more neuron and let me try to stick to some learning rate which is reasonable and see what's happening. But hopefully make things worse. It's again getting better. Okay, but I think this is as good as it can get, right? Because what I basically did was this has drawn this line, this neuron has drawn is trying to classify the 2 points, and this neuron is basically again trying to draw another line, and these two together, it's creating this kind of three uh, stripes where the all the orange is clustered in one place and the blue is in the middle, and again there is an orange cluster. Again, I can live with this, but this is probably not the best feature representation. So I would add probably one more neuron and see how that happens. What happens then? It is still learning, so I'm not going to change anything. Something is happening.
Professor, how do you know that it's still learning? Where is the
Because
indicator?
these numbers are changing, right?
Okay. So once the numbers stop changing, means the model has learned.
It has done its best.
Okay, thank you.
Okay. Again, didn't make much of a difference, so I'm trying to add more neurons in the hidden layer. Now we are seeing something, right? So you see the training loss is progressively coming down 0.54, 0.53, 0.52. At some point, it will just plateau and it won't change again. It will just be noisy, like 0.4847, 0.4847, like that. It will keep moving. That's see now 4.645. So it is still learning. Okay. Now here's where we have to be careful because now if I let the network, it has run for probably 3,000 epochs now. Okay. Okay, around 3,000 epochs, and uh, the data set is nicely described. So what's going to happen if I train it further is this demarcation is going to get stronger and stronger. So when there is a new data point, which is somewhere over here, right? uh, it might overfit. If an orange data point, for example, spills over here, right? If I had stopped the learning somewhere before, then the model would have been better, right? So unnecessarily, I'm going on training it. I'm having more and more epochs where it had actually kind of stabilized from probably the 2000th epoch or the 1500th epoch. The further epochs were probably it trying to memorize the data. So that's where the problem of overfitting starts, right? I'm going to repeat that. So I have something here, right? See how the network will learn. I'm going to make it a little bit faster. Okay. We'll learn the way to learn yourself. It's kind of neat.
Prof, can you talk
Okay.
about at every stage what is motivating you to change variables and why? Like why are you adding the fourth neuron versus not
Ah,
adding an additional hidden layer?
yeah, because I've seen the data set, right? I've already plotted it, like the X and Y values. And in my mind, I'm thinking like something like a plus shape should best describe it, right? So, however, I'm training with three neurons. I'm not really getting I'm not happy with the output. Because, ah. So this is the best that three neurons can do. I let it plateau for some time. I let the loss flatten out. See, now the training loss is 0.67. It has remained like that for some time now. Now, if I look at this, I can still see a lot of spillover of the blue points here, yellow points here, and there is an unnecessary blue point. I don't know where that's coming from, right? So I'm not really happy with this. So that's my motivation to add one more neuron. And the loss never, I was not happy with the number, the 0.6.06 or whatever. Okay, so I was just looking to see if I can reduce the loss function given let's say. So I added one more neuron and I'm training it again. Okay. Um, See, that's another thing with neural network. The first time I ran with the same four neurons, you remember what happened? Uh, I was able to move up to 0.47 in my training loss. Now it kind of seems stuck at 0.06, and even the shape is very different from what we got before, right? So everything is now dependent on everything is dependent on the random weight which was initialized when the neural network started training. So that particular weights which fix that particular model was based on its own weight initialization, right? Now, second time when I ran it, it is running with a different set of weight initialization. So it never went to that place where the previous network went, the previous model went, right? So I can actually start over and see if I can get the same model again.
And this is the trial and error that you were referring to in the last session.
Yes, exactly.
Got it.
So when we try to train a network, we train it a couple of times because we are kind of dependent on the first initial weights that it started with. Now it's giving an entirely different shape, you see. And the training losses point to, I mean, we got better numbers last time. Probably because the learning rate is high. So I'm changing the learning rate and see to see if that makes any difference. No. So it is stuck somewhere in the local minima. It is not able to get out of there.
Prof, at what stage would you say it's overfitting?
Ah, so but what that's what I wanted to replicate actually, but that didn't happen. Never mind. So here, what I will do is I'm increasing the. I'll come to that question in a minute. Okay. So it seems to have stuck at the local minima. So I'm trying to include a decay and I'm trying to change the weight suddenly. So it's in the learning rate. See now what has happened. I let it get out of that local minima by increasing the learning rate. So I basically said, now get out of that, take a huge step jump from that place which you are in the latent space, that no error space to some other point. So that's what it did exactly. Jumped out of there to a new position, and from there it is learning again. Right? So this is a pretty decent network with a loss of 0.04 and kind of this shape. Now, when would I say it is overfitting? When I find a huge difference between the training loss and the test loss. So if my training loss is 0.46 and my test loss remains at 0.08 or something, then I would be worried. The difference between my training and test loss, that's my indicator for over the power footing. Okay. Did it answer your question?
Yes, absolutely.
Okay.
And training loss and test loss have no relation to how, so of course to each other, but no relation to how close we can minimize them. Like, are we not trying to optimize minimization for both?
We want the training loss and the test loss to be as close as possible, but we're not looking at a particular number,
Got it.
right? So if my training loss is 100, if is zero, then almost definitely I am overfitting.
Oh, that exactly, yeah, that's what I meant. So like I
Yeah.
tried to add a fifth neuron, and my training loss came down to nearly zero, and I was definitely overfitting.
Yeah, correct. Yes. Okay. So I'm taking a second approach. I'm seeing if adding more non-linearity will fix my problem. So I'm going to have just two neurons and one neuron in my second middle layer and see how this turns out. Now, if you notice what happened with this one extra hidden layer, um, I was able to arrive at this much faster. In around 700 epochs, I was able to arrive at this shape, which actually took, I think, around 1000 epochs or something in my previous case, right? So let me add one more hidden layer, one more neuron in the hidden layer, and see what happens there. See now the network has done its best. It's 0.198. The training loss is 0.198, right? So then we had one more hidden layer. Now. At this point, I'm just fishing. Okay, so I'm just trying to see if uh, well, now how would you comment on this? I'm going to quickly take a screenshot of this one. Okay. In 500 bucks, I was able to get this shoe. Okay. And I'm going to use the number of $200. See, now I'm getting a very different shape from what I got before. And that's only around 300 bucks actually. Right? So now the training loss is so minimum 0.006. Okay. Screenshot. Stabilized here and download within your. Okay. So I have three images now. I'll put them one next to each other. Give me 1 minute. Okay. Now let's hear your comments on the three networks that we trained. This is three hidden layers. Or okay, forgot to know. I think this is the one with three hidden layers. And this is the one with two hidden layers. And this is with one hidden layer. Which one would you trust and why? So we trained three neural networks. My first network, second and third network. I think this was with four neurons, one hidden layer. This was with two hidden layers and three and two in each. First hidden layer had three neurons. Second hidden layer had, I think, two. And this was, I think, two and two and one. Uh, this was two and two and one, I think.
I think I'm
So
preferring third
my
one,
question is, which one would you prefer?
the rightmost one.
The middle one.
Okay, you have to give reasons then.
Okay, the rightmost one I am preferring because coming to it is settling at a loss of zero, both the training and test, and moreover it has connected the center zone orange very well, and it has excluded the blue, and that way the performance wise, the final performance, second and third images are close, but the way it has converged is very better with respect to the rightmost one.
Okay. Any voters for first one?
We'll go out on a limb and say I would go with the left because the far right has no discrepancy between test loss and training loss. And the middle has I believe, no discrepancy as well. But the left one has discrepancy, but it's within a range that will be acceptable.
Okay, any takers for the second one, for the middle one?
Yeah, over here, I think
Okay.
the reason on the left can be a slightly higher loss, okay, but it's still excellent. The middle one looks like it's very low training and low test loss, but not too perfect looking. The right one looks perfect and impressive, but it may be overfitted, over complex, or maybe just lucky. So I'll go with the middle one.
Okay. So usually we don't have access to the figure since there are only like two input features. We got this nice scatter plot. Usually it's very difficult to find a scatter plot with all the input features, right? So I will go by the figures firstly. I would go by the test loss and the training loss, the numbers. Okay. So if I want to go just by the numbers, I would go with the left one, the leftmost one. Here is something in the chat box. First one, okay, Rio, thank you. What are we optimizing for? So we are optimizing for, yeah, correct. That's the question. So I would optimize for the metric that I am actually monitoring. I am monitoring the loss function here. So the training loss is 0.0006 here, which is very less. The test loss is slightly more, which I would expect 0.009. Okay. So maybe these two, they actually describe the data much better. But I would rely on this model more because let us say I have a data point that comes over here. Okay. Now I don't know if that is blue or if that's going to be orange. It's right in the center, right? Or somewhere over here where there is a little bit of ambiguity. Okay. So now I want to use a model which I can rely on in the sense that if an ambiguous data point comes, I should be able to at least say that okay, no, my model will perform like this in case of ambiguity. Now here I have no room for that. I am saying that my model is 100% perfect. Okay. And my model is 99% perfect or 99.99% perfect. Okay. Which is a very dangerous claim as somebody who is building a model. Right. And my test loss, my biggest giveaway is my test loss is also 99.99, which means that the model is doing the exact same thing for seen data points and for unseen data points. Okay. I would feel safe using a model which where there is some room for ambiguity. So here I'm saying I'm 99%, 99.994% accurate in my training, but I'm slightly less accurate in my test, which is how real world data is going to be. If an ambiguous point comes, which is over here, you see this model has actually classified that as an ambiguous point. It's not saying that it's ambiguous, but it at least knows that okay, it's somewhere in this gray area. It's neither blue nor this orange area. I would I would feel comfortable working with a model that says that rather than arbitrarily placing a blue point in the orange area because it's overconfident for an unseen data point. Is that clear? So I would go with the leftmost. Did I convince the others who gave a different answer? Yes,
Yes.
yes.
Question, sir, is you also pointed out the epoch, this number of cycles
Mhm.
that it took for us to get there basis the learning rate.
Yeah,
Would the computation power required also be a factor in this consideration because that would inform cost
definitely.
well?
Definitely. So, I mean, every epoch is more computation, right? So definitely, computation wise, the number of epochs is one thing. Um, we'll see that tomorrow actually, when we actually make construct a neural network, we'll see how many trainable parameters are there in a network. That actually gives away the computation rather than the number of epochs and other things.
Got it. Thank you.
Leo, no.
Yeah, I actually made that decision based on the shape of the loss.
Mm.
Uh,
Okay.
because it seems like
The
it's
shape, 1
learning.
minute. Just 1 minute.
Yeah,
The shape
it's
of this or the shape of
yeah
this?
the
This
rate
one.
of the rate of
Okay.
the
Yeah.
loss dropping. So it seems
Okay.
like
Yeah.
it is learning well right from the start. So does that play a part in how you select other than what you mentioned just now?
Yeah. So basically, correct. So I would rely more on how it's falling. And we unnecessarily think trained a lot of epochs here. We could have as well stopped here. In which case, we'd have gotten that nice fall rather than the steep fall which we see here. The steepness is because of the number of epochs. I agree with you. Yeah.
Yeah. Thanks.
The others, people who suggested the middle and the left one, I hope I've convinced you that I would feel comfortable with the leftmost one because there is room for ambiguity there, which is how a real world data point is actually going to be.
Professor, is the leftmost as simple as the one in the middle? Simple in the structure,
Simple in terms of what?
number of neurons and layers.
No, no, no. I think these three are three different architectures.
Mm-hmm.
So this was, I think, four neurons and one hidden layer. This was, I think, two hidden layers and three and two neurons in each. And this was basically three, two, and one. Three hidden neurons in first layer, two hidden neurons in the second layer, and one hidden neuron in the last layer. That was the architecture of this one.
Okay.
I could have taken the screenshot along with the architecture, but I'll
Yeah.
leave it there. Yeah.
Yeah. Yeah.
Next time we'll do that.
Thank you.
Okay. Okay. So I think at this point,
Yes.
okay. At this point, let's move on and let's just take this one data set because it's really interesting. I'm just going to start with an arbitrary set of neurons. You see, this is a very complex data set, right? At least spiral. So say how it's slowly getting there. Or not so much, right? So I'm going to add because now at this point I feel that there are it's too complex, so I'm just going to add a lot of neurons. And since I'm going deeper, I'll probably change this to ReLU and let us see.
Hello, Professor.
Yeah.
Yeah,
Is there
may
anything
I
happening?
understand? Yeah, may I understand the dataset dimension is still we consider still in two-dimensional because it is visualized on the plane, although they are distributed in spiral form.
Yeah. Yeah. So, I mean, this is just a representation, correct? It's probably multi-dimensional, but the number of input features x1, x2, that's what we have.
Thank you, thank you. Got it.
So it's slowly getting there. I'm going to increase the learning rate. Probably not so much. So should we add more hidden layers? Probably that will work. See now how my learning rate just killed the network, right? So I changed it to 0.1 and it didn't converge any longer. Just resigned. Or something good going on and I ruined it, I guess. So starting. Okay, I'm going to add more input features, increase the dimensionality. Let's see how that works.
Prof, is the model assigning weightage because it knows the underlying data set, because it's allowing us to customize weightage as well right now?
So the weight is always learned, so it's not assigned. It starts with random numbers, and as the network learns, it gets optimized.
Got it.
So are you happy with this data set, with this model now? Or should we add one more anyway? I think I'll stop with this and let you explore it when you have time. I think eventually this will converge at some point.
Yeah, Professor, I think just now the one before
Yeah.
is about the
Yeah.
best fit, the best spiral result so far.
Yeah, that was the best one, right? So now it's
Yes.
completely gone. No point in. You see, once, I don't know if you noticed a couple of things that I did now. The learning rate was too small, so I increased it. And when I went back to my original learning rate that worked in the past, it didn't work. Why? That's because in my during my gradient descent, it was actually going down in one direction. But I gave a different learning rate and I forced it to move to some other location. But it got so far off that it had to start again at a different learning rate. So the network did not uh, uh, work with the original learning rate that I actually had, right? I hope you noticed it when I was actually training it. Yeah, Rio.
Yeah, is it okay if I just share my uh, screen?
Oh, you want to share your screen? Yeah, okay, go ahead.
Yeah, thank you. Yeah, so this was mine. I added more neurons, but what I wanted to ask is for the output, this particular loss graph, right? I actually continued more epochs, and then there was a sudden spike over here. So what can I make out of this? Because when there was a spike, the obviously the fit was thrown totally off
Um,
this
so
part.
yeah, so a couple of things. I think if the network is actually converging and if there's a sudden spike, maybe it got to like a plateau in the latent space, and it actually in the further epochs it's started retraining. Like if you remember the gradient descent videos of. So if you remember the gradient descent figure that I had that I shown in the previous lectures, I'll open the gradient descent one much.
Is it because of the topography of the
Of the space, yeah.
lost surface? Yeah.
Yes. So if you remember this figure from the previous class, okay. So probably converging and and at some point it probably got off some plateau or somewhere and it started retraining again. Yeah.
Okay. All right. Thank you.
Okay. So Jeff has two hidden layers, 6 and 4 neurons, and that looks good. Yeah. Okay. So yeah. So basically, we can have multiple architectures arriving at a particular solution, right? The only thing we should consider is which of those is prone to overfitting. We can keep adding hidden layers that technically should describe the data best. But as you keep adding hidden layers, your network also gets increased risk of overfitting. Okay, so the best would probably be having less hidden layers and more not too much, but kind of more neurons in your initial layers so that the neuron is actually specialized at what it's doing rather than making complicated non-linear transformations within the hidden space. Okay. All right. So quickly, I'll start with the next topic, the next module, which is okay. So this is called from categories to embeddings, transforming data for enhanced learning. That's the module name. So we'll basically be looking at different ways in which we can transform data for to feed into the neural network. Okay. We've now covered basic forms of neural networks, different functions that it can basically do. Now we are slowly moving towards what type of data we can use for neural networks, right? So till now we were looking at structured data, Excel sheets, numbers, but not always Excel sheets are in the form of number. We have to convert those text or whatever is there into some form in which the network can make sense of it, right? The more meaningful numbers we give to the network, better will be our goal. Okay. So that's where we are converting a category into something called embedding, and we'll see what an embedding is. Before that, can somebody describe what is your idea of an embedding? It is a very common term nowadays, right? So people hear embedding all the time.
Finding the right position for placing in a multi-domain vector space.
Okay. Something less jargony, if that's possible.
Embedding is, it could be inserting one module from one location into another module that does not congenitally fit, but you create a method to fit it in.
Okay. So two things don't get along usually, but you find a way to make them get along, and somehow you feed that number rather than just the raw numbers.
So we're
Right.
converting into numbers, just converting meaning into numbers.
So converting meaning into numbers. I think that I will stick to that description of embedding. So instead of just giving raw numbers, we are just giving numbers with some meaning or some hidden meaning to it. Yeah. So that is, I would call embedding for now. I hope you can see the slides full screen. Okay. Okay. So as you would know, a neural network doesn't really understand category names or sentences. Uh, a neural network is basically a number machine, right? So it can find, it can change, it can reduce numbers, it can play with numbers, but not with names and sentences as we have in our regular data nowadays, at least. Okay. Um, so a neural network basically learns the structure from the number, like different set of numbers, they create a pattern, and that's the pattern that a neural network is going to learn. So basically, I think I'll stop with this slide. The core problem for us when we deal with some sort of a text data is some non-numbers are easy to convert to numbers, right? For example, if I have region as south or west, east or north, then I can basically give some code to it. So 0 means south, 1 means north, 2 is east, and 4 is west, or go clockwise, or whatever works. Channel, online, in person, in phone, through WhatsApp, there are different channels of communication in marketing, let's say. Again, I can assign numbers to them. If there's a gold customer or some credit card customer who's silver, platinum, so I can assign a tier. And remember, when I say south, north, east, and west, they probably do not have a hierarchy. There is no order to that, right? Even channel, probably there is no hierarchy or order. It is just a way of recording things, and online or offline or through WhatsApp or through SMS. But tire is a slightly different game, right? Usually there's a hierarchy. When you talk about the tier of customer, there are silver tier, gold tier, platinum, and whatever. Even the class in which you travel in a flight, there's economy class, business class, then first class, and all this. So there actually the number has a meaning. So one is better than two, two is better than three, and so on. Okay. Now, I'm sure you have dealt with this in the past in your ML and your other sessions. There are ways to convert those numbers into some sort of numbers with meaning in a way that preserves the hierarchy, the order, and also in a way that the hierarchy or order is it's broken. Okay. What am I talking about? What kind of encoding am I talking about? To break down the order or hierarchy of the numbers in categorical variable.
Ordinal, you mean to say, process?
Yeah, ordinal or yeah. When it's ordinal, when it's not ordinal. Have you heard of one-hot encoding?
Yes, yeah. Usually we use for categorical.
Yes. So what does it do? Does it preserve the order or it does not preserve the
It
order?
does not. It does
Does
not.
not, right?
Yeah.
Correct. Do you know any encoding which will preserve the order?
Numerical encoding.
Yeah, so the numerical encoding will actually preserve the order of the variable, but not encoding will actually not preserve, right?
Yeah.
So we have ways to deal with it. There are certain places where we know how to handle text data, like in such cases which I just described. There's a mathematical representation, and some patterns are learned from that. But text is slightly different, right? So when I say the service was excellent, but delivery was late, here the encoding is more a design choice rather than assigning numbers to it, right? How many words are there in English language? Is that a very difficult question?
We could tell them.
Yes, it is. How can we actually say how many words are in use in that?
Right?
Maybe
Let
more
us
than
let us say there are 60,000 words. Okay.
oh my god.
So one way of encoding text is actually just assigning a number to the text. If that is human, that is number 5326. Text, the word text is represented by the number 3246. Service is represented by 33,000 whatever. Okay. So that is one way of doing it, right? Of dealing with the text data. Is that efficient?
No, it will keep running out. I mean,
It's yeah,
Yes, it
even
is.
actually it might be deficient in the sense, let us say there is a company which has like 50,000 products. Okay, but that might actually be very close to the number of words in a given language. May not be English, but there are other languages, right? But
Yes.
the problem with language is the inherent variation which we say. So, for example, good is very related to words. It's also very related to the word better, right? The word office is probably related to the word desk and pen and laptop, right? What happens when we assign random numbers to these texts is the relationship between the text is not preserved, right? Which means that for the neural network, the word banana is as different to peel as it is to the word ocean. But semantically, we know that the word peel is closer to the word banana than the word ocean, right? So here, encoding becomes more like, should I just give the word and assign the number associated with the word, or should I actually come up with a system which preserves the meaning of the word? Okay, that is the big question in this module. Okay, this is also a very short module. We will be revisiting this module again. Like for the autoencoder, we are going to keep revisiting it when we do image segmentation, when we do other stuff. We will come back to it. Okay, but I want to leave with this question as to what would be the best way to represent numbers, represent text? Would it be just the random number assigned with the text, or have some meaning associated with it? Okay. And I think with that, I will end the session today. Okay. And I think I'll end the session today. I think I'm 2 minutes beyond time. I'm sorry for that. Any questions?
So, Professor, just now you mentioned number is a better representation, right?
Yeah. That's because the
You
neural
can
networks
classify it,
understand only numbers. Yeah.
right? So let's say like a word like king and queen
Yeah.
and prince and
Mhm.
like a ruler or emperor,
Yeah.
they are
Mhm.
closely in meaning. Then you would say like a king and like banana.
Mhm.
They are very distant. Therefore,
Exactly.
the numbers will give it a proper classification.
Yes. So that's the assumption. But tomorrow we will see in what cases we need to go for a meaning based encoding versus an encoding where the meaning doesn't really matter, and different ways in which we can preserve the meaning. That's going to be the focus of the this module, the encoding module.
Thank you.
Okay. All right, great. If there are no questions, I think we can end the session for today and meet tomorrow. Tomorrow will be a lab session. So
Thank you.
thank you all.
Thank you, Professor.
Thank you. Thank you.
Thank you. Goodbye.
Thank you, Professor.
Thank you. Have a good day. Thank you. Bye.